Hello calculus fans, and welcome to section 3.6, where we talk about derivatives of logarithmic and inverse trig functions. In this section we use implicit differentiation to find derivatives of log functions and inverse trig functions. So hopefully section 3.5 went well when we talked about implicit differentiation. But before we get started, we need to review logarithms. So let me just mention some of the rules of logarithms. So we have log of a times b, log of a divided by b, log of a raised to the b power. And if you remember, logarithms were used to simplify operations. So instead of multiplying, you could use logarithms to add. Much simpler, right? Log of a plus log of b, which was a tremendous time saver when people were first starting to use logarithms, and the first logarithm table came out, which took like 20 years to compile, but it was a huge time saver once they had it. So instead of dividing, you could subtract. It's much easier to subtract than it is to divide. And instead of exponentiation, you could have multiplication. So instead of a to the b power, we could bring this b down and multiply. So these are all huge time savers. Not as noticeable today because now we have calculators that we use for easy calculations, but it was a big thing a few hundred years ago. So let's practice with logarithms a little bit. One thing you may need to do is solve an equation like this: 3 to the x power equals 12. So when we're solving for a variable that's in the exponent location, typically what we'll do is use logarithms. And we can use this rule right here. So if I take the log of each side, or the natural log, a lot of times we'll just use the natural log. So we'll have natural log of 3 to the x equals the natural log of 12. You could use common log too. Remember, common log is base 10. Really, log to any base works. But from here, now what we can do is take this x down front because of this rule. So then we have x times the natural log of 3 equals the natural log of 12. And of course, if we want to get x by itself, we just divide each side by the natural log of 3. And so we get x equals natural log of 12 divided by natural log of 3. Now we can't do any weird cancellations here. We just have to punch this in the calculator, natural log of 12 divided by natural log of 3. If you do that, you get roughly, roughly 2.26. Okay, which kind of makes sense, right? We know 3 squared is 9, so it's above 2. 3 cubed is 27, so it's smaller than 3. And just remember, when you were using logarithms, we can't cancel the logs, we can't cancel these numbers, it's just this. And if we use common logs, we would have log 12 over log 3, and if you punch that in your calculator, you get exactly the same thing. Another thing we should remember is if you have a logarithmic equation, like log base a of b equals y, there's an equivalent equation using exponents. So with the exponents, the bases stay the same, base a, and it's going to be a raised to the y equals b. So a to the y equals b. So you have a logarithmic equation and an exponential equation, and they're equivalent. Okay, so sometimes you'll see something like this, like a biconditional statement in there. So let me run through these by you guys and just make sure you're okay here. What if somebody were to ask you this question? What are they asking? So they're basically saying, what power do I raise this base to turn it into this number, right? What power do I raise the base to? Well, it's going to be 3, right? You'd say the answer is 3 because 2 cubed equals 8, right? Even if you rewrite it, you would say 2 cubed equals 8. Okay, so what about the log of 1,000? Remember, If there's no base here, it's understood to be 10, called the common log. So log base 10. So 10 raised to what power is 1,000? Well, 10 cubed is 1,000, right? So the answer would be 3. And let's see, what about, okay, how about this one? Okay, let's go this. Shake it up a little bit here. 3 raised to what power is 1/9? Well, maybe the -2 power, right? Isn't 3 raised to the -2 the same as, well, let's just check. 3 raised to the -2, that's the same as 1 over 3 squared, and that is in fact 1/9, so that works. What about log of 10? Easy, right? This is understood to be base 10, so it's got to be 1. Log base 7 of 7, 1, right? And so if you have log base e of x, we call that the natural log of x. So whenever there's this log of base e, we just write it like this, natural log. So with that in mind, what would be the natural log of e? Well, remember, it's very similar to these questions. Natural log of e is basically log base e of e, so it's going to have to be 1. Okay, what about this? A couple more. What is a log of 1? And what is the natural log of 1? Well, remember, this is base 10, so what power do I raise 10 to turn it into 1? Well, 10 to the 0 power, right? And the same thing would happen here. This is base e. What power do I raise e to turn it into 1? E to the 0 power. Okay, so I think that's good. One that we're going to use all the time is natural log of e is 1. So anytime you're walking around during your life and you hear somebody say natural log of e, what should pop in your mind is 1. Natural log of e. Did it work? Did you just feel in your brain 1? Hopefully, that's what we need. So, all right, since we have done a little review of logarithms, let's take a look at this. We've got a derivative just coming right at us right here. The derivative of log to the base a of x is equal to 1 over x times the natural log of a. And I know, if I just leave it like this, you're going to be like, now, wait a minute, Kurt. I would sure like to see a reason to believe that. And you are in luck. We have the proof right here. And don't worry, this one is short and painless. Okay, so we start off, we're just going to say this. Here's our proof. We're going to say, let's let y equal log to the base a of x. Okay, well, if that's true, I could rewrite this logarithmic equation as an exponential equation. Remember, the base would stay the same. It'd be a to the y equals x. So I can say, okay, then a to the y equals x. And then let's just differentiate this. So let's take the derivative of each side here. So I'm going to take the derivative with respect to x. So I'm going to need implicit differentiation because this is a to the y. So if I take the derivative of a to the y, I get a to the y times the natural log of a, and then also times y prime. And I take the derivative of x, I get 1. So just to remember, so I'm taking the derivative here. So think if we had y equals 3 to the x, y prime would be 3 to the x times the natural log of 3. Remember? Remember this one? So we're doing the same thing here. Our base is a, but this time y is not x. We could think of it as y as a function of x. So that's where the chain rule comes in here. So then if we want y prime, we could just do a division here and get y prime equals 1 divided by a to the y times the natural log of a. And then a to the y, well, that's just x. So then we could say, all right, so y prime equals 1 over x times the natural log of a. So there we have it. So the derivative of log base a of x is 1 over x times the natural log of a. But we might notice something. Okay, if we change this a little bit. So what if we say, let's say if we say if A equals E, okay, so if we're over here and this base is E, then we'd have this. Then we would have the derivative of log base E of x would be equal to, according to our new formula, 1 over x times the natural log of E. And we know the natural log of E is just 1, so it's 1 over x. And that leads us to this. Log base E of x is just the natural log of x, so the derivative of that is 1 over x. This is the one we'll see far more often than this one. In calculus, the logarithms we use typically are log base E, the natural log. Occasionally we'll see the common log. We don't typically use any other base, but we could in theory use any base here. But we'll see this one the most. So this derivative we have to know. We'll use this one all the time. The derivative of the natural log of x is 1 over x. Okay, we've got example 1 here. We can try our very first derivative of a logarithmic function. So f of x is natural log of x squared plus 10. So then f prime of x, well, remember when we had the natural log of x, the answer was 1 over x. So basically, the answer is going to be 1 over whatever this argument is, right? So let me just make an easy example. If y equals natural log of x, y prime 1 over x. So 1 over the input or the argument, right? So the derivative here is going to be 1 over x squared plus 10. So you have 1 over x squared plus 10. But unlike this problem where we have plain old x as an argument, so we don't need the chain rule, this is not plain old x, so we do need the chain rule. So now we need to multiply by x squared plus 10 prime, which is just 2x, of course. So this ends up being 1 over x squared plus 10 times 2x, or 2x over x squared plus 10. And I know you guys would never try to cancel these x's, right? We can't cancel those x's because there's not an x here. And I know you would never try to cancel 2's out of here because there's no 2 here, right? So there's nothing to do here to simplify. It's just 2x over x squared plus 10. So this next one, I know life is never going to be good without a little bit of trig in our day. So here's some trig. So this one, if we differentiate, we get f prime of theta equals. Okay, give it a shot. Press pause, try it out, and then check back. Okay, hopefully you pressed pause. You said, well, the derivative of a logarithm of natural log, derivative of natural log is 1 over the argument, so it's going to be 1 over sine of theta. But in this case, the argument is not plain old theta, right? It's sine of theta. So the chain rule says, all right, go ahead and multiply by the derivative of that thing. That's going to be 1 over the sine of theta. The derivative of sine is cosine. So that's really just cosine of theta over sine of theta. Right, because we're multiplying here just like we did here. When we multiplied here, this is the same as 2x over 1. So you multiply fractions straight across. This is the same as cosine theta over 1. So you multiply straight across. 1 times cosine, sine times 1. And you could leave it like that, but cosine theta over sine theta, if we wanted to, we could just write that as cotangent theta. Okay, so far these seem pretty easy. But then example 3 makes an appearance. So we need to look at example 3, and we'll try this a couple of ways. First time, we'll do it the hard way, and then we'll do it an easier way. Okay, so example 3, this one, we'll just say we're going to do this one the hard way this time. So let's say we see this problem, and we say, okay, we'll take the derivative of a natural log. Well, it's going to be 1 over the argument. But when you have 1 over a fraction, isn't that just the same as the reciprocal of the fraction? So in other words, if I had like 1 over 3/5, 1 over 3/5, isn't that just the same as 5/3? Right? Because isn't that the same as 1 times, instead of dividing, I could go times the reciprocal of 5/3, which is just 5/3. Right? So up here, when I take the derivative of natural log of this, I'm going to get 1 over this, 1 over this. But that's just the same as the reciprocal. So I'm just going to skip this step of going 1 over it like we did here. Just go right to the reciprocal. All right, so let me get this out of here. So we take the derivative. So the derivative of this is, notice the notation here, the derivative of this, right, d of this dx, so I can just say equals. The derivative equals 1 over the argument. Well, the argument's a fraction, so 1 over the argument is the reciprocal of that fraction. Right? This here is equivalent to 1 over this, right? And then, since this argument is not plain old x, now we've got the chain rule. So now the chain rule says, now take the derivative of this. The derivative of this, well, that's the quotient rule. Right, so I have to go low d high minus high d low, all over the square. The bottom we go. So low is x minus 5, d high. So the derivative of high, the derivative of the numerator is 1, right? I just put a 1 here. So low d high minus high, which is x plus 3. D low, I need to take the derivative of this. Well, x minus 5 under the radical, that's really x minus 5 to the 1/2, right? So when I take the derivative of this, I'm going to get 1/2 x minus 5 to the 1/2 minus 1, which is minus 1/2. And then, since that's not plain old x, you take the derivative of that, which is still 1. So it doesn't really matter too much. But when I take the derivative here, I'm going to get times 1/2 x minus 5 to the minus 1/2. And then again, times the chain rule, which is the derivative of x minus 5, which is just 1. Okay, then we go all over the square of the bottom. Well, the square of a square root, that will cancel, so we'll just get x minus 5 down there. Okay, so let's see what we've got here then. Well, there's a lot of things we could do here. The algebra is going to get a little intense here, but do you see how this, we could think of this, actually let me write something that'll make it a little easier. I'm going to write it like, put a step in here like this. Times, now over here I've got the square root of x minus 5 minus, I guess I can leave all this the same for now, times 1/2 times x minus 5 to the minus 1/2. Okay, so since we're going to multiply here, I multiply straight across, so I have this times this. When I multiply here, I've got one term here and one term. This is all one big term. So this is going to be kind of like we're distributing. I mean, actually, we are distributing. We're going to take this, multiply here, and then here. Okay, so this is going to give us, well, think about this. When I multiply the square root of x minus 5 times the square root of x minus 5, don't I just get x minus 5? Remember, we're doing this the hard way, okay? There's an easier way to go. But this times this is x minus 5. The radicals cancel. Then I have this times this. So what I'm going to do, because this is just 1, 2, 3 factors multiplied together, multiply this into the mix, I'm going to move x minus 5 over by this one. Because then this is x minus 5 to the 1/2 times x minus 5 to the minus 1/2. So we'll add those, right? 1/2 plus minus 1/2. Because basically we're going to have x minus 5 to the 1/2 times x minus 5 to the minus 1/2. And isn't it true when these bases are the same and you multiply, you add these? which is going to be x minus 5 to the 0 power, which is just 1. So that will clean it up quite a bit. So we'll get minus, I'll put the 1/2 in front, times x plus 3, but everything else is gone. Then over here we just have x plus 3 times x minus 5. This gives us x minus 5. I'm going to distribute the negative 1/2. Then we'll get minus 1/2 x minus 3/2 over x plus 3 times x minus 5. And then we can clean this up a little bit. X minus 1/2 x is just 1/2 x, right? So you go to 1/2 x, and then we've got minus 5 minus 3/2. Well, this is like minus 10/2 minus 3/2, which gives us minus 13/2 over x plus 3 times x minus 5. And I know you guys do not like to see fractions inside of fractions, so we can fix this. Multiply by 1 in the form of 2 over 2. And that 2 in the numerator will distribute through here and give us x minus 13. So we will finally get x minus 13, and the denominator will have a 2 with an x plus 3 and an x minus 5. So that is one way to do that problem, but that is definitely not an easy way. There's a lot of algebra there. So maybe there's an easier way. Oh, look at this. That looks like the same problem we just did, but they gave us a little note here. So if you look at this note, it says, note, derivative of a logarithmic function. So what they're saying is this: use properties of logarithms, properties of logs to simplify first. So maybe we could make this a much easier problem. So it's saying take the derivative of natural log of this. Well, isn't this natural log of a divided by b? So isn't this just like saying take the derivative of natural log of x plus 3 minus natural log of x minus 5? And also, isn't this just the natural log of x minus 5 to the 1/2 power? Okay, so I'm really going step by step here, but I just want to make sure everybody's clear with what we're doing. That's really minus natural log of x minus 5 to the 1/2 power, right? Because something to the under a radical is the same as this. And then we've got that rule that says this 1/2 can come out front. So this is saying we want to take the derivative of the natural log of x plus 3 minus 1/2 times the natural log of x minus 5. And now when we differentiate, we've got a really easy one, right? The derivative of natural log of x plus 3 is just 1 over x plus 3. So we just go, the derivative of this is 1 over x plus 3. And you could say, well, it's not plain old x. This is not plain old x, so we need the chain rule, which is true. And then the derivative of x plus 3 is just 1, right? So the chain rule kicks in, but it doesn't really do much. So the derivative of the natural log of x plus 3 is 1 over x plus 3. Then we have minus 1/2 times. Remember, when we take the derivative, we can split this up and take the derivative of these individually. And the 1/2 just goes along for the ride. The derivative of natural log of anything is 1 over that same anything, right? So the derivative of natural log of x minus 5 is 1 over x minus 5. And since x minus 5 is not plain old x, the chain rule says now multiply by the derivative of x minus 5, but that's just 1. So it doesn't really do much. So this is just going to be times 1 over x minus 5. And you could stop right there. That is the answer. But because it looks so much different from our previous answer, I'm just going to continue, just so we can see that they are the same. And you don't have to do this. You could stop just like that. But if you wanted to continue just to see, we can multiply these fractions together. So just -1/2 times this. So we go straight across, and we'll get minus 1 on the top, and then 2 times x minus 5 on the bottom. And then if we're going to subtract these, remember there's this shortcut method for adding and subtracting fractions, the one that I always do, and it works with rational expressions too. I'm just going to multiply straight across. Remember, if you don't want to use the shortcut, it's okay. Just have to multiply this thing by x plus 3 over x plus 3, and this thing by 2x minus 5 over 2x minus 5 to get a common denominator. The shortcut way, though, we multiply straight across here, right? And that gives us, I'm just going to pull the 2 out front, 2 times x plus 3 times x minus 5. And then we go diagonally, so we get 2 times 1, or 2 times x minus 5 times 1. And then we go minus, because we're going to have x plus 3 times 1. So we go minus x plus 3. And then if I distribute the 2 through, we get 2x minus 10. Then distribute the negative through, we get minus x minus 3. Over 2 times x plus 3 times x minus 5, which gives us 2x minus x is x, minus 10 minus 3 is minus 13. And suddenly this is starting to look very familiar. Okay, so this is just mentioning that if you're taking derivatives and there's logarithms involved, a lot of times you can simplify this expression and then use, have a much easier derivative. And you get here, and it's equivalent to here, so we would be fine just doing it just like that. Okay, so it turns out this right here would be called the easy way. We did the hard way first. The easy way is to first use rules of logarithms to simplify the expression and then take the derivative. This leads us to a technique called logarithmic differentiation. And as it mentions here, properties of logarithms may be used to simplify the work involved in differentiating complicated expressions involving products, quotients, and powers. So if we had an expression like this and we needed to take the derivative, well, we do have the quotient rule. The quotient rule would work here, but as you can imagine, it'd be a lot of work. There'd be the product rule built in. It would be sort of a nightmare. So we can work with this one, make it a little easier with logarithms. But first note, the last one we worked on said take the derivative, and there was a logarithm already in there, right? This one, there's no logarithm here. So the note here, the important note, is that there are no logarithms in this expression. Oh, so I'll call it an equation. No logarithms in this equation. So what we're going to do is add logarithms in here. Once we have them, then we'll use them to simplify this. So I'm going to make this like a 3-step problem for logarithmic differentiation. These 3 steps we can always do, and it'll always work. So step 1, let's just take the natural log of both sides and expand using rules of logs. Okay, so what we'll do is take the natural log of this side and this side. So I'll have the natural log of y equals the natural log of that whole expression, cubed root of x plus 1, 2x plus 1 times the square root of x plus 3. Okay, well, that's equal to, because if you think about it, this is like log of a divided by b, right? We can use that rule of logarithm and say, well, that's the natural log of the cubed root of x plus 1 minus the natural log of the bottom, which is going to be 2x plus 1 times x plus 3. And if you look at this one, we're multiplying. So this is like the natural log of a times b, right? We can turn this into an addition problem. We have to be a little careful because there's that negative out front that has to distribute through. But this is going to be the natural log of, and while I'm right here, isn't it true I could write this as x plus 1 to the 1/3? Right, this is x plus 1 to the 1/3 power. And then I can expand this. So this is going to be the minus the natural log of 2x plus 1. Let's do it like this. Natural log of 2x plus 1 plus the natural log. I guess we'll do the same thing here just to save some time. Okay, so look what we did here. This is natural log of a times b, which is equal to the natural log of a plus natural log of b. I wrote this as x plus 3 to the 1/2. Got the negative out here still. So now with these powers, we can bring the powers down. I'm going to distribute the negative sign through. So this will give us 1/3 times the natural log of x plus 1 minus the natural log of 2x plus 1 plus 1/2 times the natural log of x plus 3. Okay, so we've got, I'm just going to put this back here, natural log of y. So this is step 1, which is kind of the big step. Took the natural log of both sides and expanded all this as much as we could using rules of logarithms. Okay, now we are ready for step 2. Maybe I should have put these in black or something a different color. Let's say, so this will be step 1, a little late now, but all right. And then so step 2 says take the derivative, I'll write it like this, d dx on both sides. Okay, so what that means is differentiate with respect to x on this side and this side. Now on this side, remember, this is natural log of y. Y is not x, so we can treat it like a function of x. We can use implicit differentiation. So the derivative of natural log of anything is 1 over that same anything. And then, because it's not plain old x, the chain rule comes in, and we have to multiply by the derivative of y. So when we differentiate natural log of y, we're always going to get 1 over y times y prime. And you'll do this a lot in this section. Take the derivative of natural log of y, it's 1 over y, right, because that's the derivative of natural log. But this y is not plain old x, so we need to multiply by the derivative. Then over on this other side, we have a bunch of natural log derivatives. So that's going to be 1/3 times 1 over x plus 1 minus, this one's going to be a little different. So we're going to get the derivative of the natural log of this is going to be 1 over that, same as always. But this time when you take the chain rule, when the chain rule comes into play, because this is not plain old x, when you take the derivative of this, we get 2, which we didn't get here. The derivative of x plus 1 is just 1. But the derivative of 2x plus 1 is 2, so I need to multiply this by 2 from the chain rule. And then we have plus 1/2. The derivative of natural log of x plus 3 is 1 over x plus 3. Okay, so that gets us there. I guess we could clean this up a little bit. Let's write this as 1 over 3 times x plus 1 minus 2 over 2x plus 1 plus 1 over 2 times x plus 3. Okay, that seems okay. And no, don't cancel here, right? We cannot cancel like that because there's not a 2 here. Okay, so that is the end of step 2. Now, let me just write one more thing here. So this is 1 over y times y prime. Now think about what we really want. We really want y prime. So we have to get rid of this 1 over y. So we really need to multiply both sides by y to do that. So step 3, what we want to do is multiply both sides by y. right? Because we don't want this 1 over y. So if I multiply by y, it will go away. So multiply both sides by y, and we'll get y prime equals y times all of this. All right, it's a lot to write. Plus 1 over 2 times x plus 3. Okay, then there's one more thing. Once you do that, we don't really want y here. Look at the original question. The original question is that y in terms of x. So we don't want y in the answer, but that's okay, because what is y equal to? Well, if you look back to the original expression here, we're right here. Y is equal to this. So we have to put this back into our answer. So y prime equals y times all of this. And here is y. So finally, what we want to do is take care of that y. So our final answer will be y prime equals y, which is the cubed root of x plus 1 divided by 2x plus 1 times the square root of x plus 3. And then times all of this stuff. 1 over 3 times x plus 1 minus 2 over 2x plus 1 plus 1 over 2 times x plus 3. And that is our answer. Okay. What if this has been a lot of stuff in this section? Kind of might end up being a bit of a longer video. So if you have to take a break, if this were a face-to-face class, about halfway through we take a little break. So if you have to take a break, take a little breather from all this exciting calculus. It's okay to do that sometimes. And then just make sure you come back, right? And finish this. Whenever you're in the middle of a video, you have to finish up. But this one, we finally have our answer. It looks like this. And then there's more. All right, so we've got example 6. Okay, so this one, there's a very similar way to solve this, similar to what we just did. We have to notice something about this. So this problem, there's a variable in the base and a variable in the power. Okay, so this is unusual. This one, we haven't seen something like this before. So make a little note here. The note is the exponent. The exponent is a variable, which means this is, we can't use the power rule. There's no power rule here. In other words, it's not like y equals x cubed and y prime equals 3x squared. Because if it were a power rule, this has to be a real number power, and it's not. Okay, so the power rule is out. Also, if you notice, the base is a variable. So it's not an exponential function. Right? It's not an exponential function, so we can't use the exponential rule. So we have a rule that says if y equals, say, 5 to the x, then y prime equals 5 to the x times the natural log of 5. But this doesn't work because the base is a variable also. So the exponent is a variable, the base is a variable. This we haven't seen, and this we don't really have a nice convenient form like we do for the power rule or for the exponential functions. Okay, so this one we're going to have to actually use the same technique we just used. We're going to have to use logarithmic differentiation. All right, so let's do the same thing that we did before. So I'm going to take the natural log of both sides. So the thing to notice, we've got a base as a power. We've got a variable as a base and a variable as a power. So here's what we can do every time with this. Take the natural log of each side, just like we did before. Once we do that, then we can bring this down. Right, so then we're going to have the natural log of y equals 1 over x times natural log of x. And now we're in more familiar territory now because we have something called the product rule, so we're okay here. Once we get it out of this form, we're good to go. So now we differentiate both sides with respect to x. So since this is natural log of y, but not natural log of x, when we take the derivative here, we're going to get 1 over y times y prime, just like before. And over here, we've got the power rule, so I'm just going to write this down. I'll write this down a couple of times. And again, there's two ways to do the power rule. There's the traditional way, and there's kind of an easier way where you just write this down twice and take turns with the derivatives. They're both equivalent, of course. So when I take the derivative of this one, the derivative of 1 over x, well, remember 1 over x is really x to the negative 1. So when you take the derivative here, it's the power, so you get minus x to the minus 2. So this would be minus x to the minus 2 times the natural log of x plus 1 over x. And now the derivative of natural log of x is 1 over x. And then this right here, minus x to the minus 2, what we can do with that, if we have minus x to the minus 2, that's really minus 1 over x to the positive 2, right? So this is really negative 1 over x squared times the natural log of x. And then these next two here we can multiply straight across to get 1 over x squared. This is 1 over x squared. And then if you look at these first two, we could multiply these and just get negative natural log of x over x squared plus 1 over x squared. Or if you really wanted to, go 1 minus natural log of x over x squared. Those are equal to 1 over y times y prime. Then, of course, if we want y by itself, we want y prime by itself, we need to get rid of 1 over y. So we multiply both sides by y. So I multiply this side by y, and it cancels. Multiply this side by y, and I get here. But, of course, y is just this thing, right? So we finally get y prime equals x to the 1 over x times 1 minus natural log of x over x squared. Now the first time you see this, it seems like kind of a lot, okay? And I get that. It does seem like kind of a lot. But when you do a few of these, you'll see they're all very similar. Take the natural log of each side, use logarithms to simplify, differentiate with respect to x, and then multiply both sides by y. It's the same over and over. But as you know, the only way to get better at these is to practice. So here's one for you. Let's have you take a minute and try this out. Now don't wait for me, right? You have to try this out on yourself to see the problems you're going to run into. This is problem number 51 from the 9th edition or 45 from the 8th edition. And let me give you a little hint on this. So as you're doing this, remember something. Sine of x over x is not the same as saying the limit as x approaches 0 of the sine of x over x equals 1. Okay, this happens sometimes when I go over this problem. Sometimes students will see this and they'll be like, oh, that's 1, but it's not. Remember, that's from a proof we did. We needed this to establish this fact, so we used the limit of as x approaches 0, sine of x over x equals 1. So this equals 1, but these two here just sitting by themselves without the limit is not equal to 1. So just kind of keep that in mind and go ahead and press pause and try this one out. Okay, welcome back. So hopefully you tried it out. So what you probably did is took the natural log of each side. And once you have that, we can use rules of logarithms to bring this down in front. So then we get the natural log of y equals sine of x times the natural log of x. And then we can differentiate, right? So same as last time, we took the natural log of each side. Then we used the rules of logarithms to bring this down. So now we have a product rule here. So we take the derivative of this side, which is going to be 1 over y times y prime, because we're taking the derivative of natural log. The natural log of anything is 1 over that anything, but this particular anything is not plain old x. It's y, which is a function of x, so we need the chain rule. Then over here, I think this time I'm gonna do the product rule the traditional way. The traditional way is first term times the derivative of the second term plus the second term times the derivative of the first term. Okay, last time we did it the other way, algebraically, they're both equivalent, so it doesn't really matter how we do it. So you get 1 over y times y prime equals sine of x times 1 over x, all right, because this time we take the natural log of x, and it is with respect to x, so it's just 1 over x, plus natural log of x times cosine of x. So I guess we could think of this as sine of x over x plus the natural log of x times cosine of x. That's 1 over y times y prime. And of course, what we really want is y prime, so we need to get rid of this 1 over y. So we multiply each side by y. I'll do this one more time like this in red, but you don't really need to. That will cancel. Multiply this by y. Because ultimately, we don't want to leave this y here, right? We've got a function that's y expressed in terms of x. So we want our answer to be in terms of x. So we don't want this y over here. But it's okay because y is exactly the same as x raised to the sine of x. So I'm just going to put this in place of y. And then we will get y prime equals x raised to the sine of x times sine of x over x plus natural log of x times cosine of x. And that is our answer. So the book also mentions page 221 and 222 in both the 8th and the 9th edition. It mentions this number e as a limit. So if you remember, we ran into number e before. We sort of defined it to be the number such that this limit was equal to 1. So we saw that before. How you typically see it defined, though, is this right here. So a lot of times this n will be a natural number or an integer. And you'll see this. And it's mainly because this comes from finance, from the number of compounding periods. That's really where E made some of its first appearances. Was from people in banking will run into this. And this is from the compound interest formula. So I'm sure you've seen from time to time, you've seen this compound interest formula where you have something like this. The amount is equal to the principal times 1 plus the rate over n. N is the number of compounding periods per year. R is the rate as a decimal. And then n again, number of compounding periods per year, times t, which is the time in years. And as n approaches infinity, so as n goes to infinity, then all of a sudden you have a equals p e to the rt. And this one you typically don't see in finance, but then you see this one in natural sciences. And these we'll see all of this up in section 3.8. So we're going to see this stuff pretty soon. But this is where e comes from. So as n gets bigger and bigger, so the number of compounding periods get more and more. So like n equals 12, like monthly compounding. And n equals 365, like daily compounding. And then as n gets bigger and bigger and bigger, this e kind of emerges from here. And you end up with p times e to the rt. But if you look at both of these, as n gets really big, we have 1 plus 1 over a really big number. So this base is really approaching 1, and this power is approaching infinity. So we're going to see later that these are indeterminate forms 1 to the infinity. This one too, this one's lesser used, but you can see that as x approaches 0, this base approaches 1, and this power approaches infinity because they have 1 over a really tiny number. So you can define e both of these ways, and it's exactly the same e as this. They're exactly the same. So the book just mentions that, maybe take a look at that if you're interested or if you get a chance. And as I said, we'll see variations of this in 3.8. But what we look at today are derivatives of the inverse trig functions. So first, let's just maybe brush up a little bit on the difference between trig and inverse trig. So if you remember when we have trig functions like sine, cosine, and tangent, when we have these, the input is going to be an angle. And the output will be a ratio of sides, right? Like in trig or pre-calculus SOHCAHTOA. So we put like the sine of 30 degrees. If I punch this in the calculator, sine of 30 degrees, and it will tell me 0.5 or 1/2. Or if I'm in radian mode, the sine of pi over 6 would say 1/2. So we're using these trig functions. Our inputs are angles, the outputs are ratios. So in this case, it's the sine of the opposite side to the hypotenuse, right, is 1/2. Now these over here, these are the reverse of that. So when you use an inverse trig, the input will be a ratio and the output will be an angle. So also remember the names here. So sometimes it's written this way. It's kind of unfortunate because it's easy to think of this as being 1/sine. But the other way, kind of the older way to say this would be the arc sine of x. Right, the arc sine of x, arc cosine, and arc tangent. So those mean exactly the same thing. Arc sine of x is the inverse sine of x. This is more common, unfortunately. The reason I say unfortunately is because this happens constantly when you're teaching. You'll see students using this, and they'll think of it as, oh, it's 1/sine of x. Because in plenty of other cases, that is exactly what it means, but it doesn't mean that here. It's not the multiplicative inverse like it looks like. So, yeah, it's just unfortunate, but arc sine of x is the same as this. So in this case, to get back to talking about inverse sine, we would say something like the inverse sine of 1/2. So our input is a ratio, and the output would be 30 degrees, right? Or could be pi over 6 if we're in radian mode. Okay, so those are the differences. We've got regular trig functions and inverse trig functions. And if you want to review inverse trig, if you want to do a quick review, let me just make a note of this. Inverse trig is in section 1.5. So for a quick review of inverse trig, you can look in the Stewart Calculus textbook, section 1.5. It will review a little bit. And also, just to make really clear, I just want to make this really clear, the inverse sine of x is equal to the arc sine of x. They're exactly the same, and it is definitely not equal to 1/sine of x. Okay? Okay, so what we're going to do now is talk about the derivatives of these inverse trig functions. So let me make a little room here. And we have to recall something about this. Y equals the inverse sine of x means that the sine of y equals x, and also means that y is between negative pi over 2 and pi over 2. So when you first looked at these inverse trig functions, you took a regular trig function like sine and you restricted the domain so that you would force it to be a one-to-one function. And so that's where this comes from. So if we start from here now, if I take the derivative, let's say I start from this statement right here, the sine of y equals x. All right, so if y equals the inverse sine of x, then the sine of y equals x. And if I take the derivative here, the derivative, the sine of y, if I just start right here and differentiate, I would get the cosine of y times y prime, because y is not plain old x. That equals 1, right? So cosine of y times y prime equals 1, because I'm differentiating this too. And then if we solve for y prime, we'd get y prime equals 1 over the cosine of y. All right, and also, since we're over here, and this y is between negative pi over 2 and pi over 2, so we could say since y is between negative pi over 2 and pi over 2, well, then cosine of y is going to be greater than or equal to 0. And just think of a cosine graph here. This is pi, and this is negative pi. Well, we know the cosine graph goes through at pi halves and negative pi halves, right? It goes something like this. So as long as we're between negative pi over 2 and pi over 2, this cosine is going to be greater than or equal to 0. Okay, so then we could say, so from the trig identity, sine squared y plus cosine squared y equals 1, we have cosine squared y equals 1 minus sine squared y, which means that cosine of y, if I take the square root, I'm going to get 1 minus sine squared y. And I don't need to worry about the negative root, because I know that cosine of y is greater than or equal to 0, because we're on this range here. And then we also know this. So 1 minus sine squared y, but sine of y is the same as x. It's because sine of y is the same as x, we could say cosine of y is equal to 1 minus x squared. Okay, so cosine of y is 1 minus x squared, and therefore we could say this. Therefore, if y equals the inverse sine of x, then y prime equals 1 over 1 minus x squared, right? Because y prime equals 1 over cosine of y, and this is cosine of y. So that gives us our first derivative. If y equals the inverse sine of x, or the arc sine of x, y prime will be 1 over 1 minus x squared. So we've got three derivatives here to fill in. So the first one, we actually did this one. We showed that the derivative inverse sine of x is 1 over the square root of 1 minus x squared. You could use a very similar argument, and they may ask you to do this in the homework for the inverse cosine. And see that it's very similar, but as a negative 1 over the square root of 1 minus x squared. And then one more that we won't show, but that we also have to know, is the derivative of inverse tangent, and that is 1 over 1 plus x squared, no radical. Okay, and then there's a little note here. It says, we don't need to know the derivatives of the other three inverse trig functions. Nobody really uses those. Also, it sort of depends on how you define them. So remember, to have an inverse function, you have to make your original function 1-to-1. And there's not really a lot of agreement on how to handle that with secant, cosecant, and cotangent. So we don't need to really know these. So let me just make a note. So these other three, the other three would be like inverse cosecant, inverse secant, and inverse cotangent. I've never seen them used before, not that they couldn't be, but everything that we need we can get from these three right here. Now, if you're curious though, if you want to read a little bit about this in the Stewart book, on page 223 in the 9th edition, let's say in the 9th edition, page 214 in the 8th edition, you can find information about those. But again, the answer completely depends on how you define these, and there's generally not agreement about how to define those. Remember, you have to make them one-to-one. So people change they use a different range for these when they do that. But it's a lot of work that you don't need, because everything we need we can do with these three right here. Okay, so speaking of these three right here, let's try example number 8, which says y equals the square root of the inverse tangent of x and find y prime. All right, so first I'm just going to rewrite this as arctangent of x raised to the 1/2, because then we have the power rule, right? Just like if somebody said we've got y equals x to the 1/2, you would say, okay, so y prime is 1/2 x to the minus 1/2. Something very similar will happen here. We use the power rule first. We get 1/2 this to the 1/2 minus 1, which is minus 1/2. And then the chain rule says, since this is not plain old x, you need to multiply by the derivative of that. All right, so we get y prime equals 1/2 inverse tangent of x, or arctangent of x, to the minus 1/2. Then the chain rule says, now multiply by the derivative of that thing. And that we just figured out. Or, well, maybe we didn't figure it out, but we just saw it up here. So that's the derivative of that. So that would be 1/2 inverse tangent of x to the minus 1/2 times 1/1 plus x squared. Which I suppose you could leave it like that. But what we'd probably do, if this problem were in the back of were in the book and you looked in the back, they would probably change this to 1/, inverse tangent of x to the positive 1/2, and then they'd probably put it under a radical. So the answer would probably look like this. Numerator would be 1. Denominator would be 2 times the square root of inverse tangent of x, and then times 1 plus x squared. So that is a decent amount of material, and I think you should be all set on section 3.6. So as you know by now, I'm sure, the only way to get good at these problems is to practice. So it takes a lot of practice. So keep working on the homework, and as always, let me know if you have any questions.